Question 3, Part A. In the diagram, ABCD is a quadrilateral. The equation of the line AD is 2x minus y minus 1 equals 0. Part 1. Show that ABCD is a trapezium by showing that BC is parallel to AD. To prove that two lines or intervals are parallel to each other, in other words, they're running in the same direction, we need to show that the two gradients are identical. Let's consider the gradient of interval BC. Now we have the coordinates of points B and C. And because we have those coordinates, we can use the 2-point gradient formula to find the gradient of interval BC. That is y2 minus y1 in brackets divided by x2 minus x1 in brackets. Change in y divided by change in x. So the gradient of interval BC is given by 5 minus 3 in brackets divided by 1 minus 0 in brackets, which equals 2. Hence the gradient of interval BC is 2. Let's consider the gradient of interval AD. Now we have the equation of AD in general form, which is 2x minus y minus 1 equals 0. So to find the gradient of interval AD, we need to rearrange this formula into gradient intercept form. That is y equals mx plus c, where m represents the gradient of that interval. So rearranging this equation to make y the subject, I'm going to move the negative y here from the left-hand side over to the right-hand side, which is an easy way to isolate the y. So we have 2x minus 1 equals y, but we should write the equation with the subject on the left-hand side. So y is equal to 2x minus 1. We just switch the two sides around. Now that's in the form y equals mx plus c. Hence the gradient of AD is 2. So gradient BC is equal to gradient AD, hence BC is parallel to AD. Therefore ABCD is a trapezium because we have one pair of opposite sides parallel. Part 2. The line CD is parallel to the x-axis. Find the coordinates of D. It is given that the interval CD is parallel to the x-axis. That means the points C and D are the same height above the x-axis, which implies that their y-coordinates are identical. So the y-coordinate of D is equal to the y-coordinate of C, which equals 5. Now the point D also lies on AD. Now we know the equation of AD, which is 2x minus y minus 1 equals 0. So the x-coordinate of point D is found by letting y equals 5 in the equation 2x minus y minus 1 equals 0 and solving for x. Hence 2x minus 5 minus 1 equals 0, which gives us the equation 2x minus 6 equals 0 when we combine the like terms here. Now moving the negative 6 over to the other side, it becomes positive 6. We get 2x is equal to 6. Dividing both sides of the equation by 2, we get x is equal to 3. Therefore, the coordinates of point D are 3, 5. Part 3. Find the length of BC. Since we have the coordinates of points B and C, we can use the 2-point distance formula to find the length of BC, since we treat BC as the hypotenuse of a right-angled triangle. So BC squared is equal to 1 minus 0 in brackets squared plus 5 minus 3 in brackets squared. So we get BC squared is equal to 5. Taking the square root of both sides to make BC the subject, we get BC is equal to the square root of 5. Therefore, the length of BC is the square root of 5 units. Part 4. Using the perpendicular distance of a point from a line formula, D equals the absolute value of AX1 plus BY1 plus C over the square root of A squared plus B squared, show that the perpendicular distance from B to AD is 4 over root 5. The equation of line AD in general form is 2x minus y minus 1 equals 0. And the coordinates of point B are 0, 3. To find the perpendicular distance of a point from a line, which incidentally represents the shortest distance from that point to that line, we use the perpendicular distance formula. That is, the perpendicular distance D is equal to the absolute value of ax1 plus by1 plus c over the square root of a squared plus b squared, where a in this case is the coefficient of x, which is 2, the b is the coefficient of y, which is -1, the c is the constant term, which is -1, the x1 is the x-coordinate of point B, which is 0, and the y1 is the y-coordinate of point B, which is 3. So D is equal to the absolute value of 2 times 0 minus 1 times 3 minus 1 over the square root of 2 squared plus -1 in brackets squared. So the perpendicular distance is 4 over the square root of 5 units as required. Part 5. Hence or otherwise, find the area of trapezium ABCD. To find the area of a trapezium, we need the lengths of the two parallel sides and the perpendicular distance between them. Now in trapezium ABCD, the two parallel sides are BC and AD. Now we know the length of BC, which we found earlier, and that's √5 units. We also know the perpendicular distance from point B to AD, which represents the distance between the two parallel sides here, and that's 4 over √5 units. Now AD forms the base of trapezium ABCD, and we need to work out the length of that base. Now we have the coordinates of points A and D. Now the coordinates of point D we also worked out earlier. So using the 2-point distance formula, the length of AD is given by AD squared is equal to 3 minus 0 in brackets squared plus 5 minus -1 in brackets squared, which gives us the equation AD squared is equal to 45. Taking the square root of both sides to make AD the subject, we get AD is equal to √45 or 3√5 in simple surd form. So we have the lengths of the two parallel sides and we have the height or the perpendicular distance between them. So we can use the area of a trapezium formula, half times the perpendicular height times the sum of the lengths of the two parallel sides, A plus B. So that equals half times 4 over √5 times √5 plus 3√5 in brackets. Now these are like terms which we can combine and we get 4√5, and half times 4 over √5 gives us 2 over √5. So multiplying these two terms together, the √5s will cancel. We end up with 2 times 4, which gives us 8. Therefore the area of trapezium ABCD is 8 square units.